Hello, my name is Samantha Middleton, and this is a video presentation for my third year individual project entitled In-situ CO2 Biomethanisation, a feasibility study investigating equipment needs and economic and environmental impacts. The British government has recently announced plans to have net zero emissions from energy generation by 2050. To achieve this, there will need to be an increase in the number of variable renewable energy sources, such as solar panels and wind turbines, being constructed in the country. These sources do not generate constant electricity supply, as they are dependent on light intensity and wind speed, which are both inconsistent and unpredictable. As a result, there will be times when electricity will be produced in excess, and other times when the electricity produced does not meet demand. Grid balancing methods are used to ensure that electricity produced by variable renewable energy sources can consistently meet the demands on the national electricity grid. This involves storing electricity at times of surplus production and using the stored energy when supply drops below demand. In-situ biomethanisation is one possible method for grid balancing. The surplus electricity is converted into hydrogen and then methane. This methane can then be stored and used in gas power plants to produce electricity when supply from variable renewable sources is insufficient to meet demand. Storing energy as methane rather than hydrogen has a number of advantages. Firstly, methane has a much higher storage density, allowing more energy to be stored in a given volume. Methane is also more compatible with the existing infrastructure, allowing it to be more easily converted from gas back into electricity. This report investigated the feasibility of CO2 biomethanisation by using Southern Water's Millbrook wastewater treatment plant as a case study. At the Millbrook site, anaerobic digestion is used in the sewage treatment process. The biogas produced is used in an on-site combined heat and power plant, which provides sufficient electricity to operate the entire site. This report specifically investigated upgrading pre-existing anaerobic digestion sites to perform in-situ CO2 biomethanisation. The following basic layout was applied to the Millbrook site, and 4 distinct variations were investigated. Electricity from a renewable source is used to power an electrolyser. The electrolyser then produces hydrogen, which is pumped into an anaerobic digester. Typically, biogas produced by anaerobic digestion has a methane content of around 60 to 70%. This increases to up to 95% methane content when produced through CO2 biomethanisation in this way. Biogas produced in the digesters then follows one of 2 routes. Some biogas will be pumped into Millbrook's combined heat and power plant to produce the electricity required by the rest of the site. The remaining biogas will be upgraded to biomethane by removing carbon dioxide from the biogas mixture. The biomethane is then added to the national gas grid, where it can be used by houses for heating or by gas power plants to produce electricity when required. The project investigated 4 variations on this basic arrangement, using no storage, storing hydrogen before it enters the digesters, storing electricity in a battery to power the electrolyser, and storing methane as liquid biomethane for use as a vehicle fuel. These options had varying feasibilities when applied to the Millbrook site. Storing electricity or hydrogen is infeasible, as there is no large variable renewable energy source nearby, and there is not enough available space on site for the battery or hydrogen storage tanks. Producing liquid biomethane for fuel is also infeasible, as the biomethane output from the site is too low to justify building a liquefaction plant, and again, there is insufficient space on site to do so. Only the no storage option will fit on site, and the electrolyser must be powered using national grid electricity. For this to be used in a grid balancing scenario, energy from the electrolyser must only be drawn when the supply of the grid outweighs demand. Currently, this does not occur for frequent long periods of time, but if a larger proportion of the grid is supplied by variable renewable sources, these instances may increase, making this option more feasible. To give a rough idea of the costs involved in operating the no storage CO2 biomethanisation site, the cost of the electricity used by the electrolyser were compared with the profits received from selling biomethane to the grid and from the government's renewable heat incentive. The cost per kilowatt-hour electricity used in this example assumes that all electricity is purchased from the national gas grid at their prices. This value was chosen because it would represent the worst-case scenario, though it can also be seen that even purchasing electricity at half of this price will result in an economic loss at Millbrook. There were two major conclusions drawn from this project. Firstly, Millbrook is not a feasible site for CO2 biomethanisation. There is no renewable electricity source nearby able to power the electrolyser, so the costs of the process are too great for it to be implemented, and there is also very little available space on site for the extra equipment. The second conclusion is that any site which will implement CO2 biomethanisation must have a large renewable energy source nearby, which can supply electricity at a lower price than the electrical grid. This includes sites which have been upgraded, as described in this project, but also purpose-built CO2 biomethanisation plants. The next steps for this research would be to conduct similar studies using sites which better meet the requirements, specifically having nearby renewable energy sources and more available space. Further research into the effects of CO2 biomethanisation of varying input hydrogen volumes would also help to develop a better understanding of the process and its operating limits.